Our heuristic methods work quite well within the ORAN framework.
My name is Sophie Paulin and I'm leading Work Package 3 in the MARSAL Project. The goal of this work package is to integrate ORAN with a cell-free radio access network. In this demo, we are showing the result of our integration with IS Wireless and Acceleran, who are collaborating in this work package. The demo is provided to you and explained to you by Robert Beerten, who is a researcher in my team that has been heavily involved into the MARSAL project and demo implementation.
We will showcase the proof of concept 1.1 in the MARSAL project. What is the context? The proof of concept is centered around the concept of cell-free massive MIMO. Previously, users were only served by a single access point in the network. More recently, researchers are also exploring the concept of having every user served by every single access point in the network. But even more recently, we have experienced that this type of network is really inefficient and ultimately unscalable. The concept of user-centric cell-free massive MIMO has been proposed, where users are served by only a small subset of APs. What is the problem? In a user-centric cell-free massive MIMO network, the selected initial cluster for a user becomes suboptimal as users move away from this cluster. Thus, the cluster needs to be reconfigured in function of the new position of the user. This is our central problem in this proof of concept. We reformulate new clusters when users move away from the initial cluster. We have developed a solution within the ORAN framework. What exactly is this ORAN framework? In the past, the base station was just a single entity. Nowadays, in the ORAN framework, this base station is divided into the radio unit, the distributed unit, and the central unit. Additionally, we also have a RAN intelligence controller, which allows for network-wide optimization. In this context, we have developed our testbed to allow connections via an E2 interface. Thus, we can optimize our testbed based on an ORAN-based near real-time rig. Here you see our testbed. It consists of 64 antennas and 32 radios, 8 access points with 8 antennas each. This is our user equipment connected to a different radio unit.
The testbed is actually a traditional collocated massive MIMO testbed that allows to communicate to 12 user equipments both in the uplink and the downlink. To achieve downlink communication, as you all know, we need full phase coherency, very good synchronization, and reciprocity calibration. So this is all included. What we did with the testbed is to distribute it. So we could use it as a cell-free radio access network. To distribute it, we have distributed both the processing elements and the antennas. And the antennas, as Robert has explained, organized in 8 radio units, each with 8 antennas. The concept of the demo is actually to show 2 things. We want to show that we can do the signaling from the testbed to the near real-time rig, and that the near real-time rig can do the user to RU allocation for a cell-free setting. For this demo, we have distributed our 8 radio units in our lab and in the corridor of our building. To do this, we have one user that sends pilots to the 8 ORUs. These compute some metrics that are sent to the DU that then sends this further to the near real-time rig. Based on these messages, the near real-time rig will decide on an ORU allocation matrix. We have 2 algorithms in the near real-time rig. One is a cellular algorithm. In this case, the near real-time rig will allocate a single ORU to the user. And we have a user-centric cell-free algorithm. And in this case, the near real-time rig will allocate a selection of ORUs to serve the users in the downlink.
In this packet trace, we see the messages from the base station after they are translated to the specific E2 interface and how they are then communicated to the near real-time rig. Conversely, we also see how the near real-time rig communicates with the DU and how this then ends up in the base station.
To show the impacts of the near real-time RIC decisions on the user equipment, we have developed a Grafana dashboard. On this dashboard, you can see at the top the downlink signal to noise ratio received by your user. Below, you see the input to the near real-time RIC, which show the 8 measurements from our 8 distributed radio units. At the bottom, you see a matrix that shows which RUs are allocated to the users. In our demo, we only have a single user active, so you should only look to the first column of that matrix. In a cellular configuration, you can clearly see that we always allocate only one RU to the user. You also see that when a handover happens, this has a significant impact on the signal-to-noise ratio of the user, and you see serious drops happening each time a handover is decided by the RIC. We see the drops clearly every time a robot moves from the lab to the corridor or back from the corridor to the lab.
Now I have switched the configuration of the network from working in a cellular fashion to working in a cell-free fashion. This can highlight our unique mobility management procedures that we have implemented in the near real-time RIC.
We can clearly see the improvement of the user's cell-free implementation. We see, first of all, a much more stable user signal-to-noise ratio. Even when we move from the room to the corridor and vice versa, we never have very long SNR drops. We can also see in the allocation matrix that the RIC allocates always multiple RU to our user equipment, and we see this allocation also changing as function of Robert's position actually in this case. The concept of the ORAN architecture is based on the principle that we can softwareize and containerize many of the functions of the radio access network. The idea is that we can run a cloud, an edge cloud or a regional cloud, and in this cloud we can just drop containers containing functions for the DU, for the non-real-time RIC, for the real-time RIC, etc. And the whole point of ORAN is really optimizing where these functions should run. Now we want to combine this with a cell-free architecture. And to achieve cell-free operation, we need very good real-time performance. We need very strict phase, frequency, and time synchronization. So to achieve that, we could not rely on a containerized ODU, and we had to implement the whole radio access network on FPGA. However, we managed to integrate this FPGA accelerated proprietary DU with a DU conversion layer and a near real-time RIC using the standard E2 interface. The conversion layer is provided by IS Wireless and the near real-time RIC is provided by Acceleron. Simon Pryor from Acceleron is explaining how the near real-time RIC implementation is optimized.
The movement or the mobility of the user equipment is one of the challenges of self-immersive MIMO. In MARSAL, we investigated the problem of when the users move from beyond walking to higher speeds, such as typical in a factory of robots moving around at higher speeds. And we encountered the issues with today's 5G networks based on Open RAN, where the near real-time RIC has limitations on the location of the RIC and the interfacing, the E2 interfacing, the overheads of interfacing between the DUs and the RIC that causes problems when users move faster. One of the innovations we looked at in MARSAL was taking the near real-time RIC and embedding it into the DU. So to implement what has been identified as being a real-time RIC, but currently there are no standards or no examples of these things running. So we took the RIC, embedded it into the DU, and we created a lighter weight version of the communications protocol, so the E2 Lite. And in doing so, we have shown that we can support much higher mobility, much faster speeds of users moving around to reduce the time it takes to receive the measurements and update into the RIC and update the cell-free a constellation to support this higher user mobility. Now, MARSAL does not target the extreme high speeds, but for the usage we envisage in factories, we feel that this is a very strong innovation to be able to target the types of applications where we see cell-free will play a role in 6G networks.
We have learned that managing the network under user mobility in cell-free massive MIMO can actually be achieved in the context of the ORAN architecture. We have provided simple methods which work reasonably well within this context.
In this demo, we have shown that the near real-time rig is fast and powerful enough to deal with clustering and handover management in a cell-free network. We have shown this by integrating it through a standard E2 interface with an FPGA-based radio access network implementation. A critical audience could argue that this is not a real ORAN implementation, as following the ORAN architecture, we would need a containerized ODU implementation. Achieving this for a cell-free network where timing and coherency is very important will be very challenging and will require more research, but maybe it is possible. But the most important, I think, is that we now have a real-time implementation with uplink, downlink signaling. We have shown that it can achieve very good user performance with a very simple heuristic-based allocation algorithm. But imagine what we could achieve if we would use reinforcement learning, AI methods, and much more clever algorithms in ORIC. That would be really fascinating. And that's what ORAN is promising us to achieve.